Okay. Okay, think we can start. Can you hear me? Can you hear me from your house?
Yes.
Okay.
Yes.
Thank you. Thank you. All right. So now. Record. I'm sorry. Record it. I don't know if there is an auto software here. Okay. Just a moment. I try to. Okay.
Può selezionare abilità.
Sì. Cosa devo selezionare? Ok.
Cosa acquisisci audio? Ah no, direi del microfono, scusi.
Che quello è del computer. Esatto. Proviamo a vedere le mie posizioni dello schermo. Ok. Okay. Okay, now I'm going to also register the lecture and share the screen, particularly this presentation. Okay. I hope that this is okay. Okay, we can go on with the presentation. Last time we introduced the topic of waste and of waste management in particular. We told something about the different types of waste because we defined the waste according to the source of generation, but we have seen also a systematic type of classification of the waste related to the waste list, European waste list, EWL, that is enforced in Europe and in North member states, that is able to characterize the waste according to different characteristics. The origin, the source that generates the waste, the precise type of process that generates it, and the nature, the final appearance of the waste that is the last feature that must be described. These features are described according to three couples of digits code that are able to define precisely each kind of waste. In some cases, the waste cannot be defined according to this specification, and there are some tricks, for example, to give it a number of 99 to define that it is impossible to recognize the type of waste that is under scrutiny. But there are other kinds of classification, other kinds of analysis that could be performed to understand precisely what is the waste that we are analyzing, particularly when we have to examine the mixed waste coming from household generation, household services, In this case, for example, at the entrance of a landfill or of a incineration plant, the appearance of the waste that we have in front of us is something like this that you may see on this slide. It is a mixed waste that can be classified according to different categories that can be stated before the examination according to a particular convention, according to a particular methodology. And what we are going to see now is the methodologies that can be adopted to classify the waste and to recognize the different fractions that are present inside the waste. First of all, is it a useful activity, this one? Because it seems to something dirty to do, probably not so beautiful to see. But I think that it could be useful. It could be useful for several reasons. First of all, to choose in a proper way the most effective treatment and disposal system. I have to get a precise idea of my waste if I wanted to build, to implement a proper, suitable waste management system. Okay, I have to understand if for example, the organic fraction of my mixed waste is 1/3 of the total amount of waste or 1/2, for example, because the flows, the amounts of waste could be very different, but also the characteristics that are inside the waste could be very different. We will do some examples. To size properly this system of waste treatment, it is important to understand if we have enough plants of a certain type to deal with the amount of waste that is generated in a certain territory. For example, if we have a lot of organic waste, we have to build a sufficient number of plants that are able to transform these organic waste in something else. For example, biogas or compost, humus, that could be the final product after the transformation of organic waste. In other cases, for example, if we have a lot of plastics, we could try to implement new plastic recycling activities, or if it is not possible, to recover energy from these categories that have a high calorific value. We will see also these particular characteristics of the waste. To plan separated collection initiatives, if we are able to see that, for example, the organic fraction is too much compared to other kinds of categories, other categories of waste, we could think about a new separated collection activities, initiatives in the territory in order to improve the percentage of organic waste that is collected separately, because if we collect separately the different fractions, we are able to perform a much more effective treatment of these fractions. It is always like this. The mixed fraction of waste is always the worst material to deal with, because it is often contaminated by the different pollutants that are inside the waste. And so if we are aware about a problem of a certain category, that is present in a very high extent in the mixed waste, we can try to plan new separated collection units and check the effectiveness of the separated collection initiatives that are already existing on the territory. It is so an important way to understand which type of waste we have to treat, to manage. And usually when different students wanted to make an investigation about the waste management of their countries, for example, also in many cases, students from your course raised them that want, for example, understand which type of waste management could be the most suitable for their countries. In many cases, the lacking information is the type of waste that they generate usually as municipal solid waste. And so these campaigns of monitoring are much important to understand, first of all, what is the type of waste, and secondly, which type of treatment would be the most effective to treat that waste. Usually, there are fixed categories that are defined to understand which type of waste is the one that is generated and thrown in an unsorted bin, so the mixed household waste. However, there are also subcategories that could be defined and introduced if we want a more punctual, a more defined classification of the overall waste. As far as I know, there are different methodologies in the different countries, but there isn't any unified methodology in the European Union. At least the only document that I found concerning the waste characterization is this one, methodology for the analysis of solid waste, SWA tool, that was prepared by a consultancy agency for the European Commission in 2004. And this methodology describes this approach to sample the residual solid waste fraction that is defined as the mixed waste from households and similar commercial mixed solid waste, which is co-collected. That is commonly described as daily household and commercial waste. So, in this definition, separately collected household and commercial material streams are not included in this definition, as well as small-scale hazardous waste and bulky waste. One important aim of this report is to develop a standard waste system, standard system of waste classification, since it is declared in the Annex 1, at present there is no standard system of waste terminology and waste category classifications for use in solid waste analysis within the European Union. It is quite strange, but it is like this. We have not a common terminology and a waste classification system in Europe, apart from this document that dates back to 2004. So let's see some of the different categories of waste that are defined in this paper, in this report. First of all, the organic fraction of waste. This means biodegradable waste coming from kitchen and canteens, so each kind of residues and of food. For example, some examples are reported in the last column: bread, coffee grinds, cooked or uncooked food items, food leftovers, and so on, and many other categories. But in the same category of organic waste, we can include also biodegradable waste coming from gardens and parks. So all the biodegradable waste originating in a domestic garden or municipal park, flowers, fruit, and vegetable garden waste, grass cuttings, leaves, pruning, tree branches, and other parts of, let's say, yes, vegetation. There are other biodegradable waste, or this code OR103, that are all biodegradable waste not applicable to either of the above categories, so animal remains and other kinds of waste that is left in public areas. It could be inserted in the organic waste also this category, that is the wood fraction of waste. But in general is classified as a different part, a particular fraction. Wood could contain untreated wood or treated wood. For example, we have this kind of wood that are simply cut from trees, or also untreated pallets, sorry, like this, bottle corks, for example, also. But we have also some treated wood coming from, for example, furnitures, wardrobes, something that is contained in a house, or also some wood that is related to the railways, that is usually dirty of oil, of other pollutants that could be that have fallen from the trains. Obviously, these are two kinds of different. These are two kinds of different wood, because the first type of wood is simply an organic one and could be, for example, composted. That it could undergo biological degradation as well as the organic fraction that we have seen before. While the treated wood must be recycled with some particular processes, because it contains, for example, varnishes, paints, some other kinds of materials, for example, inside, some parts of iron or something like this, or glues that could be that could contaminate this fraction. Other particular category of waste is the paper and cardboard fraction. Also among the papery wastes, there are differences that are reported in this classification. For example, in this case, we have high gloss paper or card and wallpapers. This high gloss paper is not biodegradable. Okay, it is used, for example, for magazines, for some photographic papers, and must be recycled together with other papers, and usually it cannot be obtained paper that could be used again for newspapers, for magazines, or something like this, but could be transformed, for example, in cardboards, in packaging waste. There are other kinds of waste, for example, paper card used for packaging, all non-glossy paper card packaging, cereal packets, cleaning product cartons, all you can see in the markets that contain other stuffs and are used as packaging. The newspapers that are a particular type of waste paper, usually they are already produced with recycled paper, because in many cases you have a fraction of recycled paper also in the paper that composed these newspapers. Other paper and card non-packaging, for example, birthday type cards, books, computer printouts, diaries, envelopes, and other kinds of paper, also toilet papers. Usually it is more difficult for toilet papers to recycle. Plastics. Plastics is a very broad category of waste because, you know, when we say plastics, we are saying a lot of different categories of polymers. Okay, we will see some characteristics of the polymers and of particular recycling processes for polymers that are not simple, that are not easy, because in general, plastics could be recycled if one is so able to separate, to sort the different categories of plastics. Otherwise, you obtain a so-named plasmix that is very difficult to recycle because it contains, from a chemical point of view, many different kinds of materials. So plastics is a general definition for materials that could be also very different among each other. So there could be plastic films, for example, all packaging bags and refuse sacks, but also biscuit wrappers, cereal packets, various types of packaging. And also other plastic films that are not used for packaging. For example, cellotype, garden sheets, non-packaging films, plastic bags, refuse sacks, shopping bags, and other kinds of films. But, for example, also in other examples are reported here for dense plastic bottles or jars or other kinds of packaging. In the first category, you may insert the alcoholic drinks, detergents, laundry liquids, milk, many other beverages also. While dense plastic other packaging could contain, for example, cleaning tubes, cosmetic tubes, egg boxes that are formed with other kinds of polymers. But interestingly, there is also a final category of plastics, for example, represented by music or video cassettes that are quite old but are still present in the separate collection of plastics that are usually very difficult to recycle, even though they are collected together with the other plastics. And in general, these parts are not are removed from the flows that goes to the recycling plants and usually are burned because they have a high calorific value and they could be effectively recovered as thermal energy. As for the glass, also in this case we have different kinds of category. Maybe you know that it is very difficult to recycle different kinds of glass together. Okay, The brown type of glass contains different additives than the green type of glass and the clear one. And so you may, if you wanted to obtain a effective recycling, you may collect together, separately all these glass. But at least in Italy, we have not different containers for the different types of glass. So we put all together and generally there is a step of separation, further step of separation after the collection, through which it is possible to divide according to the colors the different kinds of glass. There are maximum thresholds of concentration of impurities inside the different flows of glass that are allowed if you want to recover effectively these materials. Usually, we associate the idea of glass with the containers of usually beverages, wine or something like this, but there could be also glasses, also in household waste that are not related to packaging, but they could be related to broken windows or something like this. Or also this television screens. Textiles are constitute another type of waste. This is a construction that was built in a Chinese fair, containing all the clothes that were discarded and that composed this kind of mountain. Obviously, it is a symbolic construction because of the textiles that are thrown away each year amount to a very huge extent of solid waste, and it's still a very big problem. We can discuss a bit about this because in general, this kind of waste is not recycled at all, and it is simply put in the landfill, or it could go in incineration plants, but it hasn't high calorific value, so it is not effective also to burn it to obtain energy. There are clothes, but also non-clothing textiles, for example, these broken curtains or other kinds of textiles, for example, carpets, and other kinds of, yes, this kind of category. Metals are quite simple to recover and also to recycle. They could be composed by a ferrous packaging fraction inside and non-ferrous packaging, for example, aluminium, copper, or other kind of, for example, tin, that constitute some packaging waste. For example, the cans or containers for some beverages that are usually sold. Here you can see also some brands, but I don't want to merchandise anything. So there are non-ferrous packaging and also other kinds of ferrous and non-ferrous materials, for example, cables or nets that could be again present in some parts of the furniture that we have in our houses. In municipal waste, we could have also hazardous waste, for example, batteries and accumulators coming from not only our cars, but also the batteries that we commonly use for small appliances. But also the used oil, cooking oil, could represent a hazardous waste coming from our houses. And then there could be also other kinds of waste that are included in the houses, for example, asbestos that was used in the past. And when there are restoration works for some houses, there could be the necessity of dispose of this kind of waste, the asbestos that is very, very hazardous. Okay, other kinds of hazardous waste are glues, solvents, medicines, and other categories that are here reported. Particularly, there are other kinds of waste that are not precisely defined only according to one category of materials. So, for example, the containers that are used commonly for juice, for milk, that are composed with different layers of different materials. The Tetra Pak cardboards are the most famous example of this kind of waste. Can be collected together with the materials that compose the highest part of the waste. So in general, for example, in Italy, we put Tetra Pak cardboards in the paper bin, together with the separate collection of paper, because in general, 75–80% of that object is composed by paper. However, inside we have some parts of aluminium and also plastic that in paper mills remain as spurious fractions that must be put in a landfill or sent to an incineration plant. There are other kinds of complex waste, for example, coming from the waste from electric and electronic equipment, named WEEE. Waste from electric and electronic equipment contain a lot of different kinds of metals and also different kinds of polymers. So it is very difficult to recover them and recycle them separately, because we would separate each kind of element or compound that constitutes this waste to obtain an effective recycling. We are concluding. This is a category including inert materials, for example, soil, stones, or other kinds of materials as ceramics, pots for flowers, other kinds of ceramic, or also bricks, materials that usually come from building and construction wastes. In general, inert materials could be easily recovered for many different applications, or also for backfilling activities. That means that we only want to fill in some parts with inert materials, for example, for the construction of roads, of streets, or other civil activities. And finally, this is the last category. The last category is, contains miscellaneous types of waste. So in this sense, you may see children's disposable nappies or other absorbents materials, some types of hospital or something similar waste, but also some fines, for example, coming from smoke activities that are, however, present in the waste, and sweeping the streets, they are collected, and so they are included in the commonly defined municipal solid waste. Okay, so this is a quite brief overview over the different categories of waste. Maybe you may have in your mind other kinds of waste that could be, however, inserted in the different categories that we have seen. But if we want to perform a waste characterization in a certain territory, we may try to make some different steps. For example, first of all, we have to describe the area of the survey in a particular way. We may define, for example, the area according to the different geopolitical districts, for example. If there are different kinds of population in the different parts of the territory, which kind of income, the type of residential structures that are in the territory, which kind of waste management practices are currently available in the area. For example, the description of waste collection systems, data of collection vehicles. These are all information that must be found in the territory. Furthermore, we can define our territory according to different strata, to different subdivisions. Okay? For example, there could be seasonal variations. Think about Rimini, that in summer increases its population by a number of 2 or 3 or something like this. So the amount of waste increases in a very significant way in the different seasons. So there could be also holiday periods. There are other socio-economic influences and collect a specific volume of bins, or a certain weight of waste, or a certain, you may collected waste according to a certain number of third person in order to have a final sample that would be representative of a certain area. Finally, you have this kind of waste, okay? The waste for the analysis could be usually screened with a screening according to a dimension of 40 millimeters, and this greater fraction could be manually sorted in the different categories that we have seen before. There could be also a further screening in order to separate all the fines, the finer fraction that are difficult to separate further. The final fraction is the fraction that is less than 1 centimeter, and while the other part could be joined with the gross waste that have been previously sorted. In this document, 13 compulsory primary criteria, and so categories, are suggested, but other 35 recommended secondary waste categories are also listed. This is a methodology that is used in Italy. You may start from a sample that has been collected by different trucks that amounts to about 3-4 tons of waste. Okay, that could constitute a typical or representative amount of waste collected in the area that we wanted to analyze. But 3-4 tons of waste is a very high amount of waste to divide manually in a second step. So you may have to reduce the amount of waste from 3-4 tons to an overall amount of about 200 kilograms of waste. How to do this subdivision and to reduce the sample to maximum amount of 200 kilograms? You may follow this procedure that is named quarterly. Quarterly means that you use generally some device to divide the cake that you have formed over a place that could be cleaned before. A cake that could be more or less half a meter, and you separate it into 4 parts, okay? 4 quadrants for equal portions. You keep 2 opposite quadrants and you reject the other 2. Afterward, you again mix all the waste and slightly rotating the axis of this subdivision, you keep the other 2 quadrants and you reject the other 2. You may repeat this procedure twice, and so since each time you are dividing your waste by 4, okay, because here you have the waste and you have again the waste, so you are dividing by 4 the total amount of waste. If you repeat it twice, if you start from 3-4 tons, after the first quartering, you reach an amount of less than 1 ton, and after the second quartering, you obtain a final sample of 200 kilograms. Okay. This is a picture taken from practical execution of this kind of procedure. Afterwards, you collect again all the waste and you put it on a screen, on a table that is that has some a screen over it that is able to divide a finer part that falls on the ground and a gross fraction that could be divided manually. Okay, you may have different bins around the table that could contain the different parts in which you want to divide your sample. Okay, and this is the procedure with which, in general, for example, our environmental protection agencies proceed to analyze the waste that is generated in the different territories. And usually this is important to understand the types of waste that are generated and can be compared with the other data other information coming from different parts of the territory. Okay, we will see some data of waste composition in Europe and also some examples of waste composition in Italy to see that there are small differences. But in general, if you look also at the waste composition in poorer countries, you may see that there are much higher percentage of organic waste inside and much less percentage of metals, of glass, of plastics, because usually the organic fraction is the main category of waste that is generated in those countries, while in the more industrialized country, you may have a higher amount of packaging, and so all the categories that are commonly used for this kind of application. Okay, we can stop here for some minutes. Okay, we will see at 10:15. He says that we wanted to understand what is the type of exam at the end of this course. I wrote some information in the previous slides, so I suggest you to see the slide in which I described the final examination. However, there will be only an oral examination, so presentation and the discussion. You can start by searching for a type of an issue, a topic that you are interested in, that you wanted to present with the PowerPoint presentation that will constitute the first part of the examination. Afterwards, there will be some questions from me and some discussion about the presentation that you will choose, okay, for your discussion. As I said to another student that wrote to me to ask some questions, you are very free to choose among the different topics of this course the one that you are more interested in. And so if you wanted to compare, for example, two kinds of waste treatment for the same kind of waste category, this could be for an example of preparation. If you wanted to examine an LCA study that contains evaluation of the environmental impact of a certain type of treatment, or waste treatment, for example, it is another example. Please do not copy and paste only the information that you find in literature, but try to critically comment the information that you find in order to make me see that you have discussed, you have thought about this topic, and for example, you have compared different sources, you have simply commented with the different remarks, the only source that you wanted to investigate. So you are quite free. If you wanted to ask to choose something and ask me a previous an early comment, you are free to do it by mail. Okay, but you are very free to choose the topic that you want. Okay, if you agree, I can go on with the presentation, and particularly with the presentation of a methodology that is in use in Italy. In Italy, we use this kind of presentation that is, this kind of methodology that has been developed by the National Research Council in Italy. It is named CNN. Sorry, okay, thank you. Okay. That consists in the operations that I described before, and in other kinds of operations that are aimed at analyzing not only the composition of the different materials that are inside the waste, but also the physical-chemical features of this waste. So after shredding the waste until a size that is less than 5 centimeters, the practitioners perform a repeated quartering operation in order to reduce the sample at a weight of about 3-4 kilograms to keep the representativeness of the sample as much as possible. Sample afterwards is dried at 105 degrees in a stub until the weight is constant. Then you can calculate the different parameters that are percentage of humidity in weight, so that is 100 multiplied by the weight of the sample before drying minus the weight of the sample after drying, divided by the initial, the final weight, and the percentage of dry substance that is complementary to the humidity, 100, and is reported again in terms of weight. Afterwards, there is another kind of parameter that is usually analyzed, that is the lower heating value. The lower heating value is a very important parameter in order to understand what is the possibility of recovering energy from our waste. Have you ever seen this kind of expression, lower heating value, or only calorific value, heating value, something like this? Are you familiar with this term? Calorific value means the amount of heat. This is the reason why it is reported as a heating value also. It is the heat or the energy that is generated by the combustion, the complete combustion of a unitary mass of the sample. Okay. So in general, if you have 1 kilogram of oil, 1 kilogram of coke, 1 kilogram of paper, of wood, of whatever you want, you may burn it and derive a certain amount of energy. Okay. Obviously, if you burn coke, you may derive a certain amount of energy that is different from burning the same amount of wood. In general, coke provides a higher amount of energy. And so the higher is the heating value, the better is the fuel if you want to burn it and to recover energy. We have some materials that have nearly zero heating value. For example, glass, for example, ceramics, because it is absolutely impossible to burn it. Okay, you can melt it, for example, glass, at very high temperatures, but it is not a fuel like coke, like plastics, for example, in the municipal solid waste, like paper, like wood. What is, in your opinion, apart from the inert materials that are ceramics, glass, also metals in some cases, which are the fractions that burn better in the municipal solid waste? Which fraction is the most combustible one? Not so. Not so good. Some fuel. Plastics are the most combustible materials in the household waste. Then there is paper generally, and also wood. But yes, also wood. While the organic fraction, apart from wood, because wood is a particular type of organic fraction, but all the organic fraction that is constituted by the food waste, for example, the leftovers from kitchens, from canteens, are very bad fuels. They have a very low heating value. There is also a difference between higher heating value and lower heating value that is quite particular, but I don't want to bore you with these definitions, so that are technical definitions, but not so important to understand what is the heating value. However, the heating value is very important to understand if residual waste could be burned effectively, or it is substantially an inert material. Some numbers, some figures about the household waste composition. This is an historical trend, starting from the last years of the 19th century. I think that the source is an English text. And in those years, the main part of the household waste was composed by dust and cinders. Okay, the one that was collected in house stuffs that were used for several applications, for the kitchen, for heating the house. And about more than 80% of the household waste generated in those years was composed by dust and cinders. There were other kinds of materials, for example, metals in very low amount, paper, kitchen and organic waste, glass, and other mixed waste. Obviously, this waste is hardly combustible, because it is composed by an already combusted material that are dust and cinders, and another fraction that is very difficult to burn, that is the kitchen and organic waste. But in more recent years, the amount of other kinds of materials, particularly plastics, inside the household waste has been reported, and not only plastic but also wood, a greater amount of mixed waste, and also of kitchen and organic waste, and dust and cinders fall to zero, more or less. So the different kind of waste generated another type of material that could be treated in other different ways. Overall, the composition of solid waste in Europe is like this, with about 18% of paper and cardboard, 12% of plastic, textiles amount to about 4%, nappies and other sanitary waste, 3%, other combustible waste, 10%, rubber, glass, steel are lesser than 5%, while the kitchen waste amounts to 25%, and together with garden waste, that is 6%, you have more or less 30% of organic waste inside the municipal solid waste. 30% is a very big percentage, because it is more or less 1/3 of the total amount of waste. So again, think about the organic fraction of waste as a critical fraction, because it could undergo particular kinds of treatment, and it is also the one that can generate greenhouse gases, if not properly treated. And usually it attacks also animals, some other kinds of drawbacks if it is not properly treated and it is left over the streets without any proper collection. So organic waste is a particularly important fraction in the overall municipal solid waste. And here, the composition of waste in Italy that is reported by the National Agency of Environmental Protection, we could say ISPRA. It is an average composition that has been calculated from 2009 and 2020. In these percentages, there also the finer part are included. And you may see that the organic fraction in this case is 35% of the overall municipal solid waste. 35% is not far from the 31% that we have seen before, containing both the kitchen waste and the green waste from parks or gardens. It is slightly higher than 31%, but we are more or less in line with the European composition of waste. 21% of plastic for European composition. There was 12% for plastic and 5% of rubber. That is something that could be similar. Also, in other combustible fraction, we may think that there could be some plastics inside. So we can say that we are more or less in line also for this kind of fraction. Sorry, 21% is here is referred to paper and cardboard, and here paper and cardboard are 18%. So also in this case we are a bit more. Plastics 12.6%, while other textiles are here 3.6%. The diapers, for example, are 4.5%, and maybe there could be a correspondence with the other combustibles that are referred to in the results of European waste composition. And finally, only to refer a quite local investigation reported here in Rimini in the different years from the middle 70s of the past century until recent years. We see that metals are quite have a quite stable trend, as well as inert materials, while we can see that there is an increasing trend of plastic materials and an increasing trend also of paper and cardboard, while there is a more or less decreasing trend of organic fraction. And this could be due both to the increase of packaging that is collected together in the mixed waste, or to the separate collection of organic waste that divert from the mixed waste part of the organic waste that is generated in the city, in the households. And these are the different trends that have been interpolated to find a trend in this composition, but it is not important. Okay, just a few words about the calculation of the calorific value that I mentioned before. To perform a combustion of the waste that you want to analyze, you may reduce the amount to more or less half a kilogram, so a very few amount if compared to the 3-4 tons of waste that we collected at the beginning of the investigation. all the reduction of the weight of the waste is performed by repeating the same quartering operation that we have seen before. For 100 grams of waste could be introduced in this calorific bomb. It is named a bomb calorimeter, in which you may calculate according to the increase of temperature that is registered after the complete combustion of the waste. You may calculate the lower heating value of the sample. Just a few examples of calorific value. Here some plastics, polyamides, polyethylene, polychloride, polypropylene, that have different heating values. So also inside the plastic category, we could have different families with a different calorific value. You may compare them with coal. The coal has a calorific value among 21 to 32. And you may see that the plastics that are inside the municipal solid waste could have a higher calorific value rather than coal. It is similar to oil, since they derive from oil. They are a sort of solid oil that we have in our houses and so in our waste. This is why it is quite profitable to convert it into energy. Natural gas, obviously, has the highest value, in value. Methane is 54. Methane constitutes the most part of the natural gas, but it is not perfectly equivalent. Cellulose has more or less 19, so quite less than the calorific value of the plastics. In general, municipal solid waste has a heating value that is around 10-11 megajoule per kilogram. And this means that apart from these categories that have a higher heating values, you may have many other categories of waste that lower this value, for example, the inert material and also the organic one, the organic fraction. Okay, in general, just a moment, yes. Okay. In general, if you want to forecast, to predict some variation of the physical-chemical characteristics of waste, you may try to calculate it according to the model that you can build of your waste composition according to different parameters. For example, if you increase the separate collection over time, you may have a variation in the different categories inside the mixed waste. If you stress the recovery of particular material fractions, probably you may have a lower amount of those fractions in the mixed waste. If you implement a separate collection of packaging, you may have less amount of packaging inside the mixed waste. So, in general, the mixed waste comes from the variation that you may have according also to some separate collection practices that you put in action in your territory that could vary the humidity, the heat value, the composition of the different fractions. This is an example, of short-term variation and mid-term variation. If you increase the separate collection of organic waste, of paper and cardboard, of glass, according to certain percentage. And in all these cases, you will have, for example, if you increase the separate collection of organic waste, you may have a diminishing trend of humidity and an increasing trend of the lower heating value. This is important to understand and to predict, because you may have the necessity of introducing variations also in the plants that, for example, burn this kind of waste. Because if the heating value increases in a significant way, at the end you may have a different plant that is able to sustain higher temperatures due to the more effective burning of waste. In other cases, you may have less need of some additional fuels for operating in an incineration plant, as we will see when we look at the examples of different incineration plants that burn household waste. But okay, this is only to say that also from the prediction of different kinds of separate collection, you may envisage also the variation of physical-chemical characteristics of the waste. Okay, there are also groups that deal with the definition of waste, the definition from a formal point of view, and also from in order to standardize all the characterization of waste in the world. For example, this committee, a technical committee of the European Committee for the Standardization, that is composed by 8 working groups that deal with different topics, different items, all related to the characterization of waste. For example, sampling techniques, leaching tests. Leaching test means what is released by the waste when it comes into contact with the water, for example. Parameters are related to species soluble in mineral acid or water. Working group that works on the terminology. The 5th deals with the analysis of waste, and other kinds of characterization are related with the other working groups. Okay, so there is a lot of work for this working group to standardize the different practices that are in use in different countries in Europe. However, this could be useful in order to know better the nature and the characteristics of waste, and finally to put in action different kinds of treatments and the recovery of waste. Okay, I finished this part, and if you haven't any question, I may go on with another, with the other part of the course that is related to the LCA. Okay. I'll share this presentation. Maybe you remember the last time that we discussed about the life cycle of the products. And we have said that in general, each product could be considered as the sum, the result of a series of actions that take place in different parts of the world, starting from the conception or the design of a new product. Then there is the extraction of raw materials, the manufacturing, the distribution, the use, and the end of life. So each of these steps could have a different environmental impact. And overall, the environmental impact could be divided also according to different types of effects on the environment. I mean, there could be effects that are displayed on a local scale, other that could be effective on a regional scale, and other on a global scale. We started seeing something about the more local effects that are we consider the solid degradation, photochemical smoke formation, and also toxicity. This was the discussion that we made last time. Just a moment, that I wanted to create a new registration. I hope that we listed also considering this these slides. Okay. Another kind of environmental impact is the acidification. Acidification, I don't remember if I already cited this this topic, but acidification is something that happens due to the emission to the air of different acidifying agents that are particularly the oxides of sulfur and nitrogen. I think that last time we discussed about the possibility of limiting the amount of sulfur in the environment by purifying the fuel in which sulfur is contained. For example, oil contains a lot of sulfur, and it could be purified, while the NOx, that means the nitrogen oxides, are emitted into the atmosphere due to the fact that nitrogen is not in the fuel, but in the air, and the air is the oxidant agent that takes part in the combustion. And when you release these acidifying agents into the atmosphere, they react with the humidity that is in the air, creating new substances that are nitric acid or sulfuric acid, that are very strong acids. This is the phenomenon that is known also as acid rain. Okay, I think that you may have heard about acid rain. It was a phenomenon that was more diffused in the past than in recent years, and it was responsible for the acidification of different parts of the world, particularly forests, Scandinavian forests, that were injured by this acidity, and they were almost completely destroyed. So acidification is an important environmental effect that cannot be reduced to a local problem, because these gases, once emitted into the atmosphere, can be transported for several hundred kilometers and so they could be referred as regional types of environmental effect. As well as eutrophication. I don't know if you ever heard about eutrophication. Eutrophication means a very good feeding of some living beings as algae, that is due to the apportion of nutrients like phosphorus and nitrogen into the environment. Phosphorus and nitrogen are very good nutrients for example, algae, that could grow very rapidly, generating the so-named algal bloom that occupies the surface of some lake or sea, for example, or ocean. This explosion of this very rapid growth of algae hinders the exchange between atmosphere and water of the oxygen. And so this provokes the death of the fishes that live in these environments due to the fact that they have not sufficient oxygen to breathe. And that could result in a large extinction, large death of many different living beings of the water. So this effect could be provoked by different kinds of nutrients that are nitrate or ammonium ions. Both nitrate and ammonium ions contain the element nitrogen. Okay. Nitrate is NO3 minus, while ammonium is NH4 plus ion. Both contain the nitrogen, that is a very good nutrient, and this could come from agricultural activities or also from the emission, again, of combustion activities. But also the emission to the environment of phosphorus in the form of polyphosphate, particularly contained in laundry detergents, may increase this phenomenon that is very critical for surface water bodies. And also this kind of effect could be considered a regional effect. But there are other effects that are commonly considered global and not regional, not local. The first one is the so-named global warming or greenhouse effect. Could you explain what is the global warming in physical terms? Why we refer usually to CO2 as a greenhouse gas, and why is it so important in increasing the temperature of the Earth? Yes, please.
Destroys the ozone layer, which is the protection from the sun, from the heat of the sun, or this one aspect of
well,
the
sun sends its energy towards the Earth, the Earth absorbs the energy from the sun rays, okay, and transforms this energy in another kind of waves with a lower energy, because we receive the energy in quite short waves that are in the visible range or ultraviolet range. The Earth, by delivering the excess of heat that it absorbed, sends in the space infrared radiations, okay? And these infrared radiation are absorbed by CO2 and other gases. So it is not directly the absorption of sun rays, of sunlight, let's say, but the absorption of the rays that are emitted from the Earth, usually in the night, but also in the day. And not only CO2, do you know what is the most effective greenhouse gas in the atmosphere? Usually we refer to this.
Methane.
What? Methane? Methane is, if we compare methane and CO2 with at the same weight, 1 kilogram or 1 cubic meter of methane and 1 cubic meter of CO2, methane is much more effective than CO2, about 30 times. But in general, in absolute terms, what is the most effective greenhouse gas that we have in the atmosphere? This is not methane.
Is it nitrogen?
No, nitrogen is not a greenhouse gas. Nitrogen has N2.
Oxygen, nitrogen.
No, there are some nitrogen oxides that could be considered greenhouse gases, but they are not in absolute the most effective greenhouse gas. It is water vapor, that absorbs a lot of infrared radiation. But obviously, water vapor is independent from anthropic activities, okay? So we usually do not consider it as a greenhouse gas that could be limited by our activities. Instead, the CO2 comes generally from anthropic activities due to all the combustion processes that occur in several human practices, because we burn a lot of fossil fuel, and the fossil fuel is a reserve of carbon that is burned and it was oxidized, transforming it into CO2 and emitted into the atmosphere. This is an oxide, nitrogen oxide, that could be considered greenhouse gas, and it contributes for about 310 times than the CO2. So 1 kilogram of N2O is considered 310 times CO2 equivalents. You may have seen that usually the greenhouse gas and the greenhouse emissions are usually reported as CO2 equivalents, because we transform each greenhouse gas emission into equivalents of CO2, okay? So you usually multiply each amount of N2O, SF6 or HFC or methane by the corresponding weighting factor, that is this one, to obtain a CO2 equivalent of those amounts, okay? Because CO2, compared to all these gas, is much less effective in absorbing IR. Why we refer to CO2 when we discuss about global warming? Because in terms of volumes of amounts of greenhouse gases in general, CO2 is the one that is emitted in the highest amount, okay? So in absolute, compared to all the others, the contribution of CO2 is the highest one in the air. However, in relative terms, there are many other climate changing gases that are much more effective than CO2. And in general, this estimation of climate change effect is still under debate, but it is already demonstrated that we have many different changes on the Earth due to the emission of these greenhouse gases. Another kind of global effect, I go rapidly into this kind of effect, is ozone depletion potential. The chemistry under this depletion has been explained in a famous paper that was published in 1974 on the journal Nature, that earned the authors a Nobel Prize, Molina and Sherwood Rowland. In 1986, there was a protocol, the Montreal Protocol, was signed by different countries in order to ban the ozone depletion substances from the production. Otherwise, the increase of the whole of the ozone that is present in the stratosphere would increase because these substances have a catalytic effect on the depletion of the consumption of ozone in the atmosphere. Ozone is a molecule that in chemical terms is expressed as O3. 3 atoms of oxygen compose the molecule of ozone, and it is quite unstable as a molecule. However, it is present in quite a high concentration in the stratosphere, and it is important for us because it stops the more hazardous radiations coming from the sun, particularly UVA, that could have a hazardous effect, harmful effect on our skin, on our body. So the presence of ozone is absolutely necessary if you want to live on the Earth. Unfortunately, the hole is increasing also in recent times, even though the ozone-eating chemicals have been banned. And finally, the resource. We have reached probably already the peak of oil in recent years. We are wasting also many other resources on the Earth, and so when we consume some resources, we have to keep in mind that these resources could not be available anymore for any other people on the Earth. Okay, this is only to conclude the different environmental impacts that could be considered in an LCA evaluation that could not be limited only to the, carbon footprint. The LCA evaluation could range over different types of environmental impacts that I mentioned in these slides. Okay. So let's stop for another brief break. We will continue in, 10 minutes. Okay. Okay. Go on. Okay, let's start again with the principles of LCA. I think that now is registering. Okay. A curiosity that I usually mention when I presented the LCA methodology is that in probably the very first study that was similar to an LCA, the case that was reported was related to a chemical industry. And it was reported in 1968, so it dates back more than 50 years. The cumulative energy requirements of some final products of the chemical industry was presented at the 7th World Energy Conference by this Harold Smith of one British chemical industry that made this consideration. I think that it is quite interesting to see which kind of assumptions they made in performing this study, because it was probably, according to some experts in LCA, the very first attempt of studying a problem from a life cycle perspective. It is said that cumulative energy is taken to be the sum of the fuel and the power directly consumed in the successive manufacturing steps. Okay, so the fuel and the power, so the electric energy and the combustible material that is used in the different producing steps. The energy that is indirectly required for the generation of the necessary power, that is interesting, because, you know, when you want a certain power from to use in a certain process, you may have it from different sources. For example, from a station that burns coal, or it burns methane, so gas or oil. But generally, the power that you use in your house or in your facility is much less than the power that was generated at the source, okay? Because there are losses of energy during the transportation from the place in which it is generated and the place in which it is used. The provision of primary raw materials and fuel, the provision of utilities other than fuel and power, and finally, the fabrication and direction of the necessary production facilities. So they took into account also the energy that was required for the building, the fabrication of all the reactors, all the facilities that were involved in a production of a certain chemical. So they took into account everything that in which a certain amount of energy was consumed. No account has been taken of the energy of combustion, which would otherwise be available from hydrocarbons which have been employed as raw materials. This is another very clever consideration, I think, because he is saying we are producing some chemical products, okay, starting from hydrocarbons that are contained in the crude oil that we use, okay? If we would transform them into CO2 and water, so if we burn them, we could have transformed them into energy. That energy of combustion would have been taken into account, but we neglect it because we think that it is not significant. However, the sentence means that they took into account also this energy, the further energy that could derive from what they took as raw materials. And the figure they produced is like this. So it is not so aesthetically attractive, but in 1968, this was the result of printed presentation. Routes to final products. So they took into account different chemical products: phosphorus, sulfuric acid, polyvinyl chloride, polyester fiber, synthetic rubber, and ammonium nitrate, considering the different steps they required to obtain the final product. And according to the amount of energy that was required by each single final product, they compared the energy with the number of steps that were required by the process, obtaining a certain trend that was quite correlated. I mean, the higher the number of steps that was required by to obtain the final product, the higher the energy that was employed in the processes. The following attempts of employing this methodology that was not known as LCA, life cycle assessment, but in other terms, in particular REPA, resource and environmental profile analysis, were conducted by practitioners commissioned for research commissioned by the Coca-Cola Company in 1969. The question was, which of the different beverage containers could be the most sustainable one, if we wanted to use another quite modern term that is sustainable, and which affect less natural resource supply? This was the question. And it is quite interesting that at the beginning of the implementation of LCA, there was some company, the very big company, that was interested in understanding the environmental impact from a life cycle point of view of its containers. And these results were never being published. And you know that Coca-Cola is very jealous about its data, its information. And also this study was never published. One of the interesting outcomes of the Coca-Cola work was that they gained a comfort with the idea of switching from glass to plastic bottles. This was the time in which Coca-Cola decided to switch from glass to plastic bottles, because previously plastics had a reputation of somewhat of an environmental villain. But this study showed that this reputation was based upon misunderstanding, even though one could say that in the glass bottle, Coca-Cola has another taste, but okay, this is not our interest in this case. Another study commissioned by Mobile Chemical Company was performed to understand if polystyrene for meat trays were really more impacting than the competing molded pulp. They used to distribute food in different canteens. I don't exactly know what was the aim of these materials, but their function was to distribute pre-prepared food. And the Mobile Chemical Company used polystyrene foam trays instead of cardboard materials that were used by a competing company. Thanks to the study, the LCA study, we would say, the mobile chemical company was able to state that their materials were less impacting than the competing materials. Why, in your opinion? Why a polystyrene material could be less impacting than the carbon materials that come from renewable sources, we could say? What is the problem? From a life cycle perspective, imagine that you want to distribute some food and you have to choose among two different materials. One is plastic and the other one is cardboard, let's say. Why would you choose plastics instead of cardboard?
Because plastic can be cleaned, maybe cardboard that is dirty, not neat, cannot be recycled.
I think that this was not the problem, because probably in both cases you had to dispose of the final the container in both cases.
Maybe for conservation.
No, because we have to imagine that they are able to respond to the requirements in the same with the same efficiency. The problem was associated with the transportation, because the polystyrene was lighter than the cardboard. And so they say, if I fill in a truck with my material, this is lighter at the end than a truck that is full of another kind of material that is heavier. So if it is true that I'm using oil to produce polystyrene, however, I'm consuming less oil in terms of diesel when I'm transporting this material to the different destinations. Okay? So from a life cycle perspective, the consumption of oil was greater in the second case due to the fact that the weight, the overall weight of this truck was higher than in the first case. So in the 60s, we have seen that there were the first studies on this so-named resource and environmental profile analysis. While in the 70s, there were the first model of LCA, particularly the Bousted model that was developed in the UK. In the 80s, there was a diffusion of this methodology, but due to the lack of standardization, since everybody could apply its own methodology to study a new case, okay, at the end there were conflicting results. Considering the same case study, one could obtain a certain result or a completely different result due to the lack of standardization. So it was a problem of using the same terms, the same assumption, the same calculations, the same models. In only 1992, CITAC, that is the Society of Environmental Toxicology and Chemistry, it is an international scientific society, published the Guidelines for Life Cycle Assessment, a code of practice. And at the end of the 90s, the ISO, International Standardization Organization, published a series of standards from 15,040 to 15,043. Afterwards, there was these standards were replaced by only two standards, ISO standards, 15040 and 15044, that were published in 2006. And nowadays, these are the standards that are enforced for the life cycle assessment. As I reported before, there were two amendments of the ISO standard 14044 that were published in 2018 and 2020. Okay, so if we wanted to define an LCA, that is the acronym for life cycle assessment or life cycle analysis, how can we express it? The European Environment Agency says this one as a glossary. Life cycle assessment is a process of evaluating the effects that a product, it mentions only products, but we will see that this methodology could be applied also to processes or to other kinds of systems, has on the environment over the entire period of its life, thereby increasing resource use efficiency and decreasing liabilities. It can be used to study the environmental impact of either a product or the function the product is designed to perform. LCA is commonly referred to as a cradle-to-grave analysis. From cradle to grave, that means that from the extraction of raw materials to the end of life of the product. It is not always like this, but in general, it is referred like this. LCA's key elements are identify and quantify the environmental loads involved. For example, the energy and raw materials consumed, the emissions and waste generated. 2, evaluate the potential environmental impacts of these loads. And 3, assess the options available for reducing these environmental impacts. Okay, also to reduce the environmental impacts, it is an important tool, the LCA, because it can compare different scenarios, let's say. There is another quite traditional definition of LCA that I wanted to show you. That is of the CTAC, the Society of Environmental Toxicology and Chemistry, definition that dates back to 1993. LCA is an objective process to evaluate the environmental burdens associated with a process, a product, activity, or service system. So it broadens the scope of this kind of methodology by identifying and quantifying energy and material used and released to the environment in order to assess the impact of those energy and material uses and releases to the environment, and to evaluate and implement opportunities to affect environmental improvements. The assessment includes the entire life cycle of the process, product, activity, or service system, encompassing extracting and processing raw materials, manufacturing, transportation and distribution, use, reuse, maintenance, recycling, and final disposal. So it mentions also the different life cycle steps that could be involved for each product, process, activity, or service system. When we talk about the life cycle assessment, we are here in this scheme. Life cycle assessment is a methodology, an analytical methodology that takes into account only the environmental aspects. Okay. If we want to consider, for example, the economical aspects, this has another type of methodology that is named life cycle costing, LCC. If we want to consider also the social aspects, because usually the sustainable development is defined as something that could happen considering all the dimensions, so the environmental dimension, the social one, the economical one. So LCA is for environmental aspects, LCC for economical, and social life cycle assessment for the social impacts or benefits. This means that LCA could be defined as environmental LCA. And sometimes you may find this expression, environmental LCA. But generally, since it was the first methodology adopted from an historic point of view, LCA stands for environmental LCA. Okay. So also avoiding the environmental term inside the LCA. But in general, these LCA, LCC, social LCA are analytical tools that are inserted in a more broader scheme that is named life cycle thinking. That means the concept of life cycle applied to all the processes, the products, the system that we analyze, that we take into account. So, for example, the life cycle thinking, if applied at the step of a project, could be defined as life cycle design or eco-design. What does it mean? It means that in my design of a new product, I take into account all the life cycle of this product. Okay? So I will design it considering possible environmental impacts that it will have in its whole life cycle. Life cycle management means something that they can manage by considering the life cycle of the different processes. Okay. So the life cycle thinking could be interpreted in different meanings. It could be an analytical tool, a design tool, a management tool, okay, according to the different application of this kind of concept. The idea of life cycle thinking is based on the principles of prevention through an impact reduction in the whole life cycle of products and services, limiting material and energy consumption and decreasing waste generation. Okay. So in an LCA approach, we completely divert from a classical economical approach. In a classical economical approach, we consider the different sectors of the activities quite separated in primary, secondary, tertiary, and quaternary activities. While when we consider a life cycle assessment, we have to include all the sectors that are involved, for example, in the production of a certain final product. Here, an example is the production of milk that is sold to consumers. We must take into account all the primary sectors, from the farming activities, from for example, the forestry to obtain the wood that can be transformed in cellulose, and finally in the cardboard that contain the milk. But we must take into account also the extraction activity of the crude oil that will be purified in different chemical plants and transformed in something that would be, again, a packaging, a container, or in some other devices, I don't know, the labels, some other parts of the final product that are necessary to sell it in the market. So all the different sectors are involved in the consideration of the life cycle assessment if we want to assess all the environmental impacts that the production of a product like this would have. Okay, this is okay, the milk supply. It is the first example. And it is very important to say that since the first applications, it was clear that this tool is characterized for what it can provide. It has no sense to compare in absolutely different materials, but only functions that can be realized. I mean, when Coca-Cola was interested in assessing the different environmental impacts related to glass, to plastic, probably also to aluminum cans, it was not interested in comparing, for example, 1 kilogram of plastic, 1 kilogram of glass, 1 kilogram of aluminum. It has no sense to compare different materials according to their weight, for example. But it is absolutely important to compare them for the functions that can be realized by using different amounts of different materials. Okay. For example, if you wanted to sell half a liter of Coca-Cola, you may take some grams of plastic, usually polyethylene terephthalate, PET, that is much lighter than the amount of glass that you use for the transportation of the same amount of beverage. Is it clear? And it is completely different from the weight that has the aluminum cans that contains the same amount of beverage. So at the end, you are not interested in understanding what is the environmental impact of, again, one unit of weight of several different materials. You want to compare a different amount of plastic, of glass, of aluminum, that are able, however, to contain the same amount of beverage. Okay. So the unit of measure that you must take into consideration is the function, not the amount of material. Okay. We will make some example to understand what is the functional use that must be taken into account in different case studies. The aim is to compare from an environmental perspective equivalent functions with the employment of different solutions or materials. If you want to travel from Rimini to Bologna, you may take a train or you can drive your car, but it has no sense to compare, I don't know, one train with one car. Okay, the environmental impact of two so different materials. You have to consider what is the function. The function is to transport myself from Rimini to Bologna in, I don't know, some minutes, in a certain time. Okay, so you may consider the impact that is related to one person transported by a car or a train, considering also the other persons that are present in the train. And finally, you can compare the two functions. Okay, the function is at the center of the consideration of a life cycle assessment. Furthermore, you may consider the different steps of the control system. Okay, In general, when we consider a product, we may start from the extraction of raw materials, okay? Extraction of raw materials, these raw materials are transformed into different components, into different semi-finished or finished products, in chemical products, and this results in a certain production of the final product. After the production, there is a step of consumption or use, and finally, after the use, there is the end of life. For each of these steps, you may see that there is an environmental release, so you have some environmental impacts due to the emission of substances or of waste, as is suggested by the W, of waste into the environment. You may have an energy consumption, so an emission of energy in the different, at the different steps. And in some cases, you will have something that could be recycled or reused, okay, in the different parts. If you consider the whole system, you may have a final environmental result, a final environmental impact of your product, for example, okay? If I want to understand what is the environmental impact of a laptop or personal computer, I may take into account from the raw material extraction to the end of life. But if you divide it into different sequence of processes, you may consider what is the step in which I get the highest environmental impact. That was the exercise that we made at the beginning of this course. So subdividing the whole system into many subsystems make it possible to understand what is the step that influences, that affects more the overall environmental impact of a product or of a process. In general, we may take into account material and energy flows. Usually energy has a very great, really great importance in determining the overall environmental impact of a product or a process. And also the emissions from the different activities. And in general, if you follow the life cycle concept, you will intend each kind of product as a set of activities and processes, a story and a history of activities and processes, each of which absorbs a given quantity of material energy, performs a series of transformation, and releases emissions of different kinds. Okay, so in brief, if we want to define what is an LCA, we could start from this very important fact that is defined by an ISO standard, by different ISO standards. It is very important that LCA have been systematized, has been standardized by the International Standardization Organization, because there are many other methodologies of investigating the environmental impacts of products or processes that have not the same importance as LCA. And the importance of LCA comes mainly from the fact that it has been written in standards that are worldwide diffused and accepted. It is a method of assessment of environmental impacts, only environmental impacts, not social or economical impacts, related to product or service process from cradle to grave, if possible. Not always, but generally it is possible. It considers both direct impacts that are those that can be usually monitored by some direct control, that are the foreground system and all the ideal systems. That is the background system. Just a parenthesis on this. Okay. And this means that, for example, if you, don't know, you have a facility which emits some gases into the atmosphere, okay, you will have a direct impact that is related to the emission of these gases. But if you use raw materials, if you use power to feed your processes, if you have some solid waste that in other places must be treated, must be located, must be placed in some landfill, you will have also indirect effects of your activities. So both systems, the foreground system and the background system, must be checked, must be analyzed if you want to have a complete picture of the environmental effects of your activities. And so LCA is important because it provides a scheme to analyze the environmental performance of single operations and of the whole system. Okay. So you can subdivide the whole system, as I said, into different steps. But it takes into account also multiple environmental impacts that we mentioned before. Also, in this case, it is important to take into consideration different impacts, and not only, I don't know, the carbon footprint, because the carbon footprint is an indicator of climate change, but there are several other types of environmental impact that must be taken into account. LCA supplies a framework to organize a conceptual dimension of data and information. When you start the study of a process or of a product, you understand quite easily that it is a very complex mixture of several single processes, unitary processes, that join together and obtain a final scheme that will be represented by different in different ways. This is one way to represent the model with different unitary processes that converge in the same place that is the final product, for example. And in general, this amount of data and amount of process is really complex, and LCA supplies a framework to understand how to manage all this information. I wanted to finish with this slide that represents the common uses of LCA. In general, to contribute to the comprehension of human activity consequences, that is a very general aim of LCA. But to compare alternative choices, this is a very important way to use LCA because the possibility of comparing different choices makes it possible to obtain relative measurements of environmental impact. Okay. Otherwise, probably I already told you this example. If I wanted to, again, to make a travel from here to another city, I can measure the CO2 equivalents that I emit into the atmosphere, but probably the absolute term of CO2 equivalents has no meaning if I do not compare it with, for example, other means for traveling the same distance. Okay, so the comparison of alternative choices probably is the best way to use LCA. Otherwise, you have, yes, different numbers, but probably they are difficult to interpret if you are not an expert. Identify critical points aimed at an environmental improvement. If you subdivide the entire process into different sub-processes, it is possible to identify the ones that affect more the overall environmental impact that you have at the end. And so if you want to improve some parts of your process, you may start from those that contribute more to the environmental impact, okay? In chemistry, we have a concept that is the speed, the rate of reaction. There are reactions that happen in two steps, okay? And so there are, for example, two steps. One of these is very quick, the other is very slow. We must work on the slower step of the reaction if we want to speed the overall process, okay? So the slow step is something that is similar to this concept. If we have 5 steps, one of them contributes for the 80% to the overall environmental impact, obviously we must start from that step to work in order to decrease the overall environmental impact. This is why it is important to subdivide in different steps an overall process. Consider a wider perspective of environmental issues to avoid the shift of the problems. Again, this has been highlighted also by the European definition. It is completely useless an alternative process that simply shifts the problem from one environmental category to another one. Okay, I can decrease environmental impact in terms of CO2 equivalent, but if I increase the toxicity release, for example, to produce the same product, I'm only shifting the problem from greenhouse gases to toxic gas. And so if I want to consider the overall environmental impact, I will avoid the trade-off, the shift of this kind of impacts from one category to another one. This is why it is so important to have a holistic view of the problem. Okay, there are other general uses, for example, to provide important information to decision makers, to let them identifying the opportunities for environmental improvements. There are more particular uses of LCA, for example, to define the performance of a product, a specific product during its whole life cycle, that in some cases wants to compare a product with a similar product that are already on the market. Another particular use is to relate a certain product or process only to a given one only environmental impact. This is the case of the studies of carbon footprint, for example, and to compare environmental performances of a product with respect to competing products or others which deliver similar services. In this case, we have to follow the same assumptions that have been made for the previous study if we want to compare them properly. Otherwise, we could have conflicting results as at the beginning of LCA application in which a standardization lacks. Okay. You got any questions? If not, I can stop the sharing this presentation. Stop also the registration. Okay. I will provide you also the link to the registration because I don't know exactly in which place, in which directory it placed the registration. Sorry?
That is on the chat.
Do you think so? Yes, I have to. Yes, to send you the proper link. Okay. Thank you. See you tomorrow. Bye bye.